All right, so as I said in class, we're going to do everything that we did in part 6. So the next thing we're going to do is confidence intervals. They still have the same format. We're still going to be looking at a point estimate plus or minus a margin of error, but we're going to change some things up because obviously we're not estimating the sample proportion. So if we wanted a point estimate for our population mean, what do you guys think we would use? Hopefully you're screaming at your computer, the sample mean. Just like the point estimate for the population proportion was the sample proportion. So if I wanted to estimate what the average GPA of a Mesa student was, I'd go out and take a sample and figure out the average of that sample. The margin of error is still a critical value times that standard deviation of our point estimate or times our standard error. But now let's think about our standard deviation of our point estimate. The standard deviation of our point estimate is equal to the original standard deviation divided by the square root of n, right? Standard deviation of our x bar. But here's where I have this weird remember. Sigma is calculated this way. You take every value and you subtract off the mean, square it, divide by n. We did this back in a Hogwarts example, Defense Against the Dark Art teachers, back in part 2. It's been forever. In fact, we've always just had our calculator do it after that one example. But the biggest issue here is that if we're making a confidence interval, that means we're trying to figure out what the heck mu is. And this formula has mu in it. So how in the heck would we be trying to figure out mu, but we somehow have sigma? This is bananas. If we don't have mu, we also don't have sigma, because sigma depends on mu. So what are we going to do instead? Well, if we had to estimate sigma, what would you use? I'm hoping you're looking back at all the other times you've estimated something. When we estimated p, we used p hat, the sample proportion. When we estimated mu, we used x bar, the sample mean. So if we're going to estimate sigma, we would probably want to use the sample standard deviation, which is S. So now if you weren't keeping track, you probably want to have like a big table of all the stuff we've learned. Because we've had our parameters or population values, and we've had our sample values, right, or statistics. And we've talked about 3 different types of measurements. We had our proportion, we had our mean, and now we're looking at standard deviation as well. And for population, the proportion was p, and the sample proportion was p hat. For the mean, our population mean was mu, our sample mean was x bar, and for standard deviation, the true value was a sigma, and our sample value was an S. So this is a table you might want to incorporate into your note card if you're having trouble keeping these all straight. So if we don't have sigma, that means we don't have the normal distribution of 7.1. So that's where part 7 gets a little bit trickier. We're going to use a new distribution called the student's T. So the student's T was developed by a guy who was working at Guinness, and he did this while he was on company time, so he went ahead and published under the pseudonym student. And he basically said, if we don't know the real standard deviation, we need to build more variability into our actual distribution. So it's still going to look approximately normal because we're still sort of dealing with the central limit theorem. So you can see the T distribution is still symmetric and centered at 0. It is still got an area under the curve of 1. Still got kind of that bell shape, right? It's very similar. It's unimodal, all that good stuff. But the big differences here are 3 and 4. It is more spread out. That's because we are dealing with that. In fact, I like to think of this more spread out is that it has fatter tails. There's more probability of being out here because we don't really truly know where we are, so we have to add in that uncertainty. And as we have larger and larger sample sizes, we're actually getting closer and closer to the normal distribution. You can see that in this picture, that the T of 2 has really fat, I meant to use a highlighter, not a pen, that's crazy. The T of 2 has really fat tails. It's a really short and squat standard looking bell curve versus the T of 9. That's a little closer to the true normal distribution. So as your n gets bigger and bigger, our estimate of our sigma gets better and better, and we don't need as much variability or probability out in those tails. So that's the student's T. I do sometimes ask questions about it compared to the normal, so make sure you do understand what its shape looks like. And otherwise, we just need to know how to use that in these questions, right? Because now that we have a T distribution, we can go ahead and figure out our formula. So by the way, we're now saying, okay, I know that this is going to be on a later page, and I'm probably getting ahead of myself, but I can't help it. Our point estimate plus or minus our margin of error, which is our critical value. Instead of a Z, we're going to use a T, times, instead of sigma, we're going to use S. So that's what our our confidence interval formula is going to look like. But we need to figure out how to find these T stars. So I'll make a second video where we go through using the T table that we've actually seen before.